A few days ago, we saw how to find the Taylor series for a specified function, but at this point, we haven't guaranteed that a Taylor series is actually equal to the function. And so today we'll spend some time looking at when it is the case that a Taylor series is equal to the function it represents. And so the idea is that last class we saw that Rn of x could be notation for the error when you use the Taylor polynomial Tn to approximate f. And if we want to say that the Taylor series is actually equal to the function, then what we really need to know is that the error in the Taylor polynomials goes to 0 as n goes to infinity. And so in other words, we can take the limit of this error function as n goes to infinity, which just means that we're taking a Taylor polynomial that's longer and longer and longer, and we can show that the error goes to 0. If we can show that, then we know that the Taylor series is equal to the original function. So as an example, we'll start by showing that cosine x is equal to its Maclaurin series, which again is just the Taylor series centered at x equals 0, and this is true for all values of x. And so in order to verify that this equation is true, we're going to want to use that Taylor error bound that we had from last class. And so as a reminder, that is that Rn of x in absolute value is less than or equal to the maximum of the n plus first derivative in absolute value, and then times the difference between the center of the series and the value that we're plugging in. And in this case, because it's a Maclaurin series, the center is 0, and then we divide by n plus 1 factorial. And so now we want to show, essentially using the sandwich theorem, that this right-hand side right here goes to 0 as n goes to infinity. And so in order to do that, we'll have to say a little bit more about this maximum of the n plus first derivative. And so for cosine, we know that the n plus first derivative is either equal to the absolute value of cosine or the absolute value of sine, just because the derivatives are sine or cosine, and we've seen this before. And in either case, we can bound that with 1. And so that means that at this point, we know that 0 is less than or equal to Rn of x, which is less than or equal to x in absolute value to the n plus 1 over n plus 1 factorial. And so now I want to take the limit of this term right here. And if I take the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial, then you might recall that factorials grow faster than exponentials, regardless of what the base is in the exponential. And the way that I can see that is that in the numerator, if I consider what happens when I increase n by 1, then in the numerator that's really the same as multiplying by x. But in the denominator, if I increase n by 1, then I'm essentially multiplying by a term that's roughly the size of n. And so if n gets really large, it will always be bigger than x eventually. And so that means that this limit overall is equal to 0. And so that implies then, by the squeeze theorem, because Rn is in between 0 and this term right here, which tends to 0, I know that the limit as n goes to infinity of Rn of x must be equal to 0. And so as a final conclusion then, that implies that cosine of x is always equal to its Taylor series.